Good morning, everybody. Today we are starting our discussion on chapter 6. So far this semester, we have learned about elements, we have learned about matter, and we know that other than having elements as pure substances, we know that there are compounds which come from those elements chemically bonding each other. And in chapter 6, we're going to learn about the two family classes of compounds, ionic compounds and molecular compounds. So let's first define what is an ionic compound versus a covalent compound. As you can see in the following slide, an ionic compound, it is actually produced from the transfer of electrons. And remember that these electrons that are going to be transferred between the elements are going to be valence electrons. And as we learned last week, a valence electron is going to be that electron that is in the outermost shell of a particular element. Now, when it comes to ionic compounds, understand that they tend to be solid at room temperature. So sometimes we also call ionic compounds salts. And ionic compounds have a high melting point when compared to the other class of compounds, which are called non-covalent compounds. So, covalent compounds, not non-covalent compounds. So, when it comes to the image that we have in the middle of the slide, the M stands for metal. The NM stands for non-metal. So when it comes to an ionic compound, understand that an ionic compound, for the most part, is made out of a metal being paired with a non-metal. In the transfer of electrons, as you guys can see here, the metal is going to transfer electrons to the non-metal. In that transfer, because the metal is losing electrons, it's going to become an ion charge. And the metal becomes positive. Now, the non-metal receives electrons, and because it receives electrons, it also makes an ion charge because it's receiving that negative charge from the electrons. That's why it becomes negative. Now, when these two charged species are interacting with one another, as you can see, that's what results in an ionic bond. An ionic bond, we don't draw it by a line. An ionic bond is actually an electrostatic interaction. Because we have that metal being positively charged and we have that non-metal being negatively charged, okay? Now, we also have another family of compounds, as I was mentioned a few moments ago, and those are called covalent compounds. Understand that another word for covalent is going to be the word molecular. So you're going to see that throughout the discussions that we have in this chapter, I may use the word covalent compounds or molecular compounds. It means the same thing. Now, when it comes from covalent compounds and we pay attention to what the figure is illustrating, you can see that there's two non-metals interacting with one another. Covalent compounds actually form by these non-metals sharing electrons, okay? When they share electrons, you can see now that one of the electrons on each of these non-metals, which is what we have in the example, are now going to be, sharing it among each other. And then sometimes we also illustrate this by saying the first non-metal, we're going to draw a line. To another non-metal, and then I'm going to write these dots around. So that covalent bond, meaning the shared electrons that these two have, I'm going to highlight it right here, that's our covalent bond, can also be illustrated by a line. Now, covalent compounds, on the other hand, tend to be soft and relatively flexible. And when we compare them with ionic compounds, they have lower melting points and also boiling points. Now, covalent compounds, as you guys will see throughout the rest of the semester, right here we are illustrating binary covalent compounds, which means that we have two nonmetals, but in covalent compounds, you can have more than two nonmetals coming together. Now, we learned last week how to identify the different classes of elements. And so we know how to classify them in terms of being a metal, a metalloid, and a non-metal, okay? I just introduced to you guys that ionic compounds tend to be a metal plus a non-metal, while covalent compounds is going to be two or more non-metals. So in part one of the in-class worksheet, you can see that I gave you a pair of elements. So if we combine them, let's now determine what kind of compound they will make, okay? So I'm going to do the first one with you guys, and then I will appreciate if you put in the chat C for covalent and I for ionic, okay? There is a question in the chat. That says, while being shared, is it always the same electrons that are shared, or do electrons randomly move from shell levels to shell levels? Does different electrons are shared? Do the electrons wear out? So when it comes to sharing, we are going to be sharing the valence electrons. So all of these chemistries that we're talking about right now is the valence electrons, those that are in the outermost shell. Now, because those are the ones that are accessible, those are the ones that we're going to see interacting, you know, being transferred in the case of ionic, or when they're shared, which is in the case of covalent, that those are the ones that are going to be in between. Those electrons do not necessarily are going to be changing energy levels, just because in these energies, as we're going to be discussing later in this chapter, the main thing is that our atoms are trying to achieve the electron configuration of a noble gas. So they're trying to have full valence shells. So those transitions of energy levels is not something that it is observed. Now, let's look at the first one. We have oxygen and we have chlorine. So when I categorize those two, oxygen is a non-metal. Let me just put it here. Nm is going to be a non-metal. M is going to be a metal. Let me use my highlighter tool. A non-metal, I'm going to highlight in yellow. The metal, I'm going to highlight in green. So oxygen is a non-metal. Chlorine is a non-metal. So when they combine, they are going to make a covalent compound. Excellent job, you guys. Let's move to the next one. Hydrogen and hydrogen. I agree, this is a covalent compound because we're talking about two things that are non-metal. Magnesium and oxygen. Great job, that's going to be ionic because oxygen is a non-metal. Magnesium is a metal. Barium and sulfur. Great job. That's going to be ionic because barium is a metal. Sulfur is a non-metal. Carbon and hydrogen. Great. That's going to be covalent. We're talking about two things that are non-metals, aluminum and bromine. Excellent. This is going to make an ionic compound because bromine is a non-metal, aluminum is a metal. Lastly, iodine and phosphorus. Excellent job. We're talking about two things that are non-metals, and that's why they make a covalent compound. So far we know how to identify it. If I'm giving a pair of elements, what kind of compound they're going to make. Now we are going to move on to actually understand in detail why is it that we see some elements that when they come together, they make an ionic compound. Then we're going to analyze it in terms of the covalent compounds. So now in section 6.1, that's a great question. There's a question in the chat about metalloids forming covalent bonds. So the majority of the examples of the metalloids, they illustrate that they make covalent compounds. Now, there are some metalloids that are known out there that depending with the other nonmetal that they're paired with, they make ionic compounds. But the majority of the metalloids, when they're paired with nonmetals, they are going to make covalent compounds. Rarely or to date, I have not seen compounds between a metalloid and a metal. What I've seen so far in my years of study and preparation in chemistry is metalloids with nonmetals. So continuing on, in section 6.1 is where we are going to learn how these specific ions, which I mentioned that are formed when we have a covalent compounds, why is the reason that they're formed, okay, and how do we call them? So I introduced to you guys the idea a few moments ago that metals are going to transfer electrons to the non-metals, okay? When they do that, they specifically will be losing valence electrons. So when you lose electrons, the analogy that I use is kind of like you're losing negativity in your life. When you lose negativity in your life, you tend to become a more positive person, and that happens to metals too. When they lose electrons, they form positively charged ions. Those positively charged ions are called cations. Please don't call them cations. That's not how you pronounce it. It is called a cation. Now, when nonmetals accept electrons from those metals, they are gaining electrons. So they're gaining negative charge. So they become negatively charged ions, and those ions are called anions. Please don't call them anions. That is not how you pronounce it. It is called an anion. So let's learn how to say it correctly. We have cations, which are positively charged, and we have anions, which are negatively charged. Now, as you can see here in the following slide, and I mentioned a few moments ago, metal elements is what mostly we see forming these cations. And here we have the example of sodium, okay? So if we look at ground state sodium, let me just do a few markings here. So this is ground state sodium. We know that the atomic number for sodium is 11. So that means that sodium has 11 protons, 11 electrons, and based on 23, it has 12 neutrons, right? But now we are going to mainly focus on the protons and the electrons. We're not going to be focusing on the neutrons. So for ground state sodium, we learned last week how to write electron configuration. And the electron configuration for ground state sodium is going to be 1s2, 2s2, 2p6, 3s1, okay? That's where the 11 electrons in ground state sodium live. So we also learned that sodium has one valence electron, and that one valence electron lives in 3s, okay? That's the valence electron in sodium. Sodium has the ability to lose that valence electron and give it to whatever nonmetal is paired with, okay? So once sodium willingly gives that electron, all of a sudden it becomes the sodium ion. We illustrate that sodium has lost that valence electron, as you can see, by just putting a +1 charge, because that's, shows that that dot that is given here, illustrating that one valence electron in sodium, has been given away. So in its place, we're going to put a positive charge because it lost one electron. So if sodium loses one electron, then its electron configuration has to change. The electron configuration for sodium ion is the following: is 1s2, 2s2, 2p6. Now, what other element in the periodic table shares that electron configuration? Not argon. Great job, neon. So it's not, let me just establish this. It's not that sodium is neon now. It's not that. It's just that now sodium has the same electron configuration as neon, okay? That's why, for those of you that have taken other chemistry courses, you have heard of gas noble configuration, because this is just illustrating that you look like this particular noble gas, okay? That's why we put the symbol of the noble gas and we put it in brackets. We learned last week that the noble gases are, in essence, those elements in the periodic table that have full valence shells. So their outermost shells are full. That gives them a specific stability. They are, for the most part, unreactive. We have a few, I think in my lifetime, I've seen a few examples, specifically with xenon, but they're mostly unreactive. I call them the yogis of the periodic table. They're very zen. They practice yoga because they don't want to be messing around with nobody. They are very stable. They have a full valence shell. Just using the analogy, they got everything going for themselves. They are energy, stabilized. So the goal of many elements in the periodic table is to have stability, okay? Because once you have full valence shells, you are not going to be, you're not going to be as reactive. You're not going to be radioactive. So at the atomic level, having full valence shell gives you a stability. Think about it like if we use the analogy of being a human person. You want to be stable. Everybody wants to be stable. At the atomic level means that you have a full valence shell. Let me correct the statement that is in the chat, not the gases. So not all gases, I'm talking about the noble gases. I'm talking about group 8A in the periodic table. It is known atomically that those elements that live in group 8A, they have full valence shells. At the atomic level, that means that when you have full valence shell, that gives you a level of stability. So many elements that are going to be either receiving electrons or losing electrons are going to be doing that because they want to reach the stability that those noble gases possess. When it comes to physical state, those are different properties. It happens to be that those elements in group 8A happen to be gases. So physical state has nothing to do with stability. It's mainly, we're talking about at the atomic level, at the subatomic particle level, actually, specifically, that if you have a full valence shell of electrons, that gives you stability. So this is the case of many metals, and in this particular example, we have sodium. Now let's look at the example of why is it that nonmetals are going to be accepting electrons, okay? So when we look at the case of nonmetals, and here we have the example of chlorine. Chlorine is going to have 17 protons and 17 electrons at ground state. Okay, now, if we look at the electron configuration, okay, of chlorine, this is going to be 1s2, 2s2, 2p6, 3s2, 3p5. Okay, those are where those 17 electrons live. Now, it is known that nonmetals can accept electrons, okay? When they are accepting those electrons, okay, that means that it depends on how many they need, right? Because it's not like they need all of these numbers. In the case of chlorine, chlorine only needs one electron to achieve noble gas configuration, okay? So when chlorine accepts that valence electron, specifically here, so when his when its 3p orbital gets full, okay, now as you can see, the seven electrons that are here, it's level 3. Let me reduce the size of my highlighter. So those 7 dots that we see there is because of the electrons that we have here in the 3s2, 3p5. So once chlorine accepts that valence electron, it becomes 1s2, 2s2, 2p6, 3s2, 3p6. That is its electron configuration. Now, what noble gas configuration did chlorine achieve? Great job, you guys. Now it looks like argon. Okay, now let me establish something else. Sometimes students think that, oh, everybody wants to be neon, everybody's trying to be argon. No, you're just trying to be like one of the elements on, you know, column 8A. It's not that all of the elements. It depends on which period you are and where you can get there. Because I want you guys to rationalize this. In the case of chlorine, okay, it can have 2 choices to achieve electron configuration of a noble gas. It can lose 7 electrons, or it can gain 1 electron. And if we think about it in terms of how many, steps it needs to take to achieve electron configuration of a noble gas, it is easier to gain that electron than to lose 7 electrons. Because if you're losing 7 electrons, that is a lot of energy that you have to put away from the atom to receive electron configuration of neon. For those students that are like, I don't get what she's talking about, think about it in terms of the periodic table. If you look at period 3 in the periodic table, the element right before argon is going to be chlorine. So if it gains 1 electron, boom, it becomes, or it has the electron configuration of argon. If it's trying to get to neon, which is in a different room, it has to backtrack 7 steps to get to neon. And that takes too much energy. Okay. So, understand, there's a question in the chat about, can you give an example where the loss of 7 electrons has actually occurred? No, I cannot do that, because one of the things that you guys will hear me say often in this class, nature is lazy. Nature wants to get to where it wants to get with the least number of steps. So it's rare that you see something losing 7 electrons unless it is a transition metal, and that's just a different ball game. So you are not going to see metals, specifically if they are from representative elements, lose more than 3 electrons. They can lose 1, 2, or 3. The transition metals are the only ones that are going to lose way more, but we will deal with those later. Remember, this is all about, you know, you're trying to achieve these things at the atomic level, but you're not trying to just make yourself tired in the process, okay? Any questions on how metals decide to become cations while non-metals decide to become anions? Excellent. Since there are no questions, let's just see how the periodic table actually helps us illustrate how these elements are going to become those noble gases that are next to them. Also, we're going to learn how the group numbers of the periodic table will be able to guide us into understanding what elements become cations, what elements become anions, and what is the number of electrons that they lose or they gain. All of this is summarized, as you can see, in table 6.2. So as I did for first week, let me just guide you that you need this table for exam 2. You need to understand this table conceptually. As I was mentioning, when it comes to group numbers, now we're going to focus on representative elements, but not all 8 of them. We are only going to focus on 6 out of the 8 representative groups. As you can see, from the metal side of things, group 1A, if we look at all of those elements that are shown there, lithium, sodium, potassium, rubidium, cesium, if you're in group 1A, you lose 1 valence electron and you become a +1 cation. Why do you do that? Because in the case of lithium, when it loses that valence electron, it looks like helium. When it comes to sodium, it loses that valence electron and becomes like neon. Potassium loses that valence electron, it becomes argon. And as you can see, it gives you in this table what is going to be the noble gas configuration that those elements get. Now, let's move to group 2A. In group 2A, elements that live in group 2A have a +2 charge. What does that mean? That it loses 2 valence electrons. And you can see with the arrows what noble gas configuration they will obtain. Now understand that these rules for 2A apply to magnesium, calcium, strontium, and barium. Beryllium, as we're going to see later in this chapter, has different rules. And I didn't mention it, but in group 1A, remember that hydrogen is a non-metal. So that's the reason why you don't see it in that column. Now, in group 3A, as you can see here, and when we look at group 3A in the periodic table, we start with aluminum, okay? Now, let's understand that when it comes to other elements there, let me just include this information. It's just that it was not given in the textbook. Gallium can also be a +3. Indium can also be a +3. Now, please don't be confused by me saying +3 or 3 positive. This is just a preference. The book utilizes the number and then the charge. I use them interchangeably. So when I write +1 or 1+, please don't be confused. I mean the same thing. So this is from the area of just looking at things that are representative elements. Again, anybody in 1A is +1. Anybody in 2A, except beryllium, is going to be +2. In 3A, they are going to be +3, but it only applies to aluminum, gallium, and indium. Now, let's proceed to the elements that are in the periodic table that live in group 5A, 6A, and 7A. So from group 5A, then we have nitrogen and phosphorus. They need to gain 3 electrons. That's why you see the 3 negative charge on them. In the case of nitrogen, when it gains 3 electrons, it looks like neon. Phosphorus, when it gains 3 electrons, it looks like argon. Understand that arsenic, which is right below phosphorus, when we look at the periodic table, is going to form covalent compounds. So that's why we don't have it in the table. In group 6A, the rules are that the elements in group 6A, they're going to be having charges of -2 or 2-, okay? Also, you can see that the rules of that -2 apply only to oxygen and to sulfur. The book doesn't talk about selenium, but these rules also apply to it. So selenium is also -2. So I'm just including these in here. Lastly, when it comes to group 7A, we have -1. So fluorine is -1, chlorine is -1, bromine and iodine is -1. And you can see also, based on the arrow, the noble gas that they are going to, or the noble gas configuration that they're going to have. In the case of fluorine, is neon, chlorine is argon, bromine is krypton, and iodine is xenon. Now, you may notice that in this table, we are not talking about group 4A. Group 4A is very interesting because in group 4A, we have carbon, silicon, germanium, we have tin, we have lead in it. And what we're going to see is that in group 4A, they're going to have variations in terms of the chemistries that they do. So because there is not a general trend, that's why we don't include it here, okay? Any questions in terms of how to determine the charge of an element when it becomes an ion, depending on its group number?
Professor, we need this table will be available, like we can use this table for the exam, right? This is something that you're going to test us on?
Yes, but it's going to be more application than anything. I'm not going to get questions out of this. The information in this table is crucial for the understanding of chapter 6. So I will suggest that instead of taking the approach of like, oh, I'm just going to have the table, memorize this information, because this information is going to come all the way through this chapter. We're going to see some of this information in chapter 7 and in chapter 9. So this information, I suggest that you guys memorize, because you will see as we progress in this chapter, it is very relevant that you know how to, by looking at the group number, you know the charge, you know what so all the information that is derived from group number, it is something that you guys need to have it under your belt for, this course. Go ahead, Victoria, question.
I have two questions. First of all, why is it important to mention the relationship to the noble gases? I understand that, we want the outer orbital to be filled, i.e. matching the 8 electrons, but why is it important to have that connection with the noble gases? Number two question is, are all protons the same? In other words, a proton that I would find in an atom of neon, is it the same kind of proton that I find in an atom of sodium?
No problem. I'll answer your question. So question number 1, why is it important that we relate these concepts to noble gases? Similar to what you make in your statement, it is just from the idea of, if we need to look at the periodic table and you're trying to look at an atom in which it has a full valence shell, you will look at group 8A. So it's kind of like using the analogy of saying, like, if you have a role model, who do you look up to?
Okay.
That's going to be the person that we are talking about at the atomic level. We're talking about the noble gases. So that's why, since they are the ones that, in a way, again, utilizing analogies, they're the ones that got it together because they have a full valence shell. They are stable. So as an atom, I look up to the noble gases. In this instance, because we're talking about forming ionic compounds, some people need to lose electrons to achieve that goal of looking like the quote unquote role model of noble gases. Other people need to gain electrons to achieve that electron configuration of a noble gas. So that's why we look at it, because that is kind of like the atom that we look towards to be like, you're stable, I want to be like you. So that's why we talk about it in terms of that. Now, the second question is, you mentioned the word protons. Remember that whenever we are talking about all of these transitions, we are not focused on the protons. The transfer that is happening here in terms of subatomic particles is electrons. So when you lose electrons, you become positive. When you gain electrons, you become negative. So to your basic questions, when we look at the protons and the electrons of sodium versus neon, they are going to be their own, right? Because we're talking about the atom. As I mentioned a few moments ago, when sodium loses its valence electron, all of a sudden it doesn't become neon. Sodium is sodium. Sodium ion is sodium ion. Now, it has something in common with neon, and that is its electron configuration. In terms of the electron itself, it's not like it's going to change shape. It's going to, change the atom, because in the system of sodium, you still have the 11 protons, which is what gives sodium its character. We are just identifying here, what are the electron transitions that are happening in order to create this charged species, but understand that the characteristics of the atom are given by the protons.
So basically, all protons are the same no matter where they're found. It's just the number of protons. All electrons are the same. It's just the number of electrons, etc.
It's what gives the characteristics. Yeah.
Oh, okay. So it's the number, but the
actual
particle is itself is the same no matter where it's found.
Yes.
Thank you. Thank you.
So we are going to now, any other questions about group number of representative elements in the formation of these charged species, which are negative or positive. Excellent. Now, another observation that has been taken from looking at what the elements in the periodic table do is that elements can have variable charges, okay? So it has been documented that transition metals, meaning the elements in group B, can form 2 or more cations, okay? That's why we call them transition metals, because sometimes they can lose 2 electrons, sometimes they can lose 4 electrons, sometimes they can lose 5 electrons. It depends on the element. And there's not a specific trend based on the group number, at least to the level of the discussions that we do in this class of how many electrons does, for example, iron likes to lose. Sometimes iron loses 1 electron, sometimes it loses 2, sometimes it loses 3. It depends on what it wants to do and the nonmetal that is going to be interacting with. And these come from the examples of the materials that we have all around us. Now, not everybody in group B is going to have multiple cations, okay? There are 3 elements in group B that only form 1 type of cation, and that is zinc, cadmium, and silver, okay? So when we look at zinc in the periodic table always loses 2 electrons, so we see it as +2. Cadmium always loses 2 electrons, so that is also +2. Silver always loses 1. So understand that even though those elements in group B can form 2 or more cations, that applies to everybody except zinc, cadmium, and silver. There's another exception to the rule. So there are some atoms that live in group 4A, 5A in the periodic table, specifically on period 5 and 6, and you can see them right here. That is tin, antimony, lead, and bismuth. So even though they're going to be living in the periodic table in groups 4A and 5A, okay, they also form variable charges, okay? In table 6.5 in the textbook, you have some examples of the different charges that these atoms can form. As you can see, bismuth can be found as +3 and +5. There's other charges that it can actually form. It's actually showing you chromium, cobalt, copper, gold, iron. Now, table 6.5, I don't want you guys to memorize. I just want you to understand the trend of the elements in group B have multiple charges except zinc, cadmium, and silver. In addition to that, the other elements that have multiple charges are going to be tin, antimony, lead, and bismuth, because we are soon going to learn how to look at chemical formulas and how to form them. So it is important that you guys keep track of like, oh, these elements, because they are in group B, they're going to make multiple charges, okay? Now, I introduced to you guys a few moments ago that non-metals are going to make anions, okay? Now, understand that there are other anions and cations that we have in terms of chemistry. And those come from the idea that we have polyatomic ions. Polyatomic ions are going to be a group of atoms that have an overall charge, okay? They typically consist of nonmetals that include phosphorus, sulfur, carbon, nitrogen, or oxygen. Now, remember, we're talking about ionic compounds. Something needs to be positive, something needs to be negative. When it comes to the polyatomic ions, understand that there's only one polyatomic ion that is positively charged, and that's going to be ammonium. And you can see here, ammonium, NH4+. The rest of the polyatomic ions are going to be negatively charged, and they can have charges of -1, -2, -3. So when it comes to the polyatomic ions, you guys need to be familiar with both of these tables. Table 6.7 from the textbook, and you need to be familiar with the table that is given on the other side, which is in the reference list for the exam. So let me just write a note here. The importance about these two tables is that you guys need to know the atoms that are in it, how many of them, the charge, and the name. So if you hear the word, for example, nitrate, you need to know that nitrate is going to be NO3 -1. It is important that you guys get familiar with these tables, because if not, the 2.5 hours of exam 2 is not going to be enough. So I encourage you guys to look at these tables, get familiar with them, know how to identify the polyatomic ions, know their charge, know their chemical formula, know their names. Why do we need all of this information? Because one of the main things that you guys also need for lab 4 is that you need to learn how to write the chemical formulas when you're given the components of that compound. Now, as you can see, we're going to learn how to write the formulas for ionic compounds. So these are the steps for writing the chemical formula for ionic compounds. As you can see, you're going to write the symbol for the metal cation and its charge. Then you're going to write the symbol of the non-metal anion and its charge. Understand that you can also have polyatomic ions being incorporated here. So I'm just going to also include it here. So rule number 1 also applies to ammonium from the polyatomic ions. Rule number 2, it can also apply to the polyatomic anions, okay? Now, in step 3, you see that we're going to take the charge, the numerical value, and we're going to make it the subscript of the neighbor, okay? You are not going to move the negative or positive. You're just going to move the value, okay? And then, if necessary, you may reduce the subscript to the smallest whole number ratio. In order to do this, we're going to do the following 3 examples together. Let's get started. So here I have the ionic compound that is going to be made from combining magnesium and bromine, okay? What is the symbol and charge for magnesium? Let's put it in the charge, in the chat. Symbol and charge of magnesium. Excellent. This is Mg. And it's +2. Remember, you can write +2 or 2+. Please don't be confused by that. Bromine. What is its symbol and charge? Is Br, and it is -1. Excellent. For those students that are like, wait, where did you guys get this from? Understand the magnesium lives in group 2A, so that's why it's +2. Bromine lives in 7A, and because it lives in 7A, that's why it's -1. That's where we got that from. We're talking about right now representative elements. Now, as I mentioned in rule number 3, the charge without the sign becomes the subscript of the other ion. So this value of 1 is going to become the subscript of magnesium. This value of 2 is going to become the subscript of bromine. So at first, we are going to write this chemical formula as Mg1Br2. Okay? Now, I'm going to write a note here.
Professor, can you repeat that again?
Give me one moment. So the values that I got there, okay, that Mg1 and that Br2 came from specifically taking the number 2 and giving it to bromine as a subscript. This value of 1, I gave it to magnesium as a subscript. So at first, I'm going to write Mg1Br2. As you saw my note, a subscript of 1 is always omitted. So my final answer in terms of what is the chemical formula for when magnesium and bromine make a compound, the final answer is MgBr2. Put a 1 in the chat if the first example makes sense. Mathematically, we can rationalize why is it that we do this exercise. Ionic compounds have an overall charge of 0. So if I rationalize it, Mg, when I have only one of them, because the charge is +2. And Br, I have 2 of them when the charge is -1. If I multiply these charges by the subscript, I find a +2 for the magnesium, I find a -2 for the bromine. If I add these 2 charges, it equals 0. Ionic compounds need to have an overall charge of 0. So that's why we're doing this whole exercise of the charges becoming the subscript. We're just doing the shortcut right away. Let's move on to the second example, calcium and oxygen. Let's put the symbol and charge for calcium. Let's put it in the chat. Calcium. Great. Ca +2. Similar to magnesium, it actually lives in 2A. What about oxygen? Great. Oxygen is a -2, -2, whichever, -2 or 2-, whichever way you want to write it. Now, understand that we have step 4. In step 4 establishes that we need to reduce the subscripts to the smallest whole number ratio. There's 2 ways that we can do this, you guys, okay? If we do step 3, we can see, oh, I'm going to do Ca2O2 again. That is because we're taking this number and we're making it the subscript out of the oxygen. This number is the subscript out of the calcium. Rule number 4 tells me that I'm going to divide by 2 So then my final answer is going to be CaO. If you don't want to bother with the division, understand that if your cation and your anion have opposite equal charges, -1 + 1, +2 - 2, like in this example, or +3 - 3, then understand that all you have to do as the final answer is just going to be the symbols of the element. The reason why you can write just the symbol of the elements is because the charges cancel each other. So since essentially the subscripts become 1 and the 1 is always omitted, that's why we can write just as the final answer CaO. Yesenia, do you have a question about why is it CaO, or are you just checking that CaO is the final answer? Oh, no problem. Put a 2 in the chat if example number 2 makes sense. Excellent. Let's move on to the third example, which is, how about if I have something or a compound, an ionic compound that has a polyatomic ion. And in this case, I'm using a polyatomic anion, okay? So you may think, for a minute, it's like, oh, wait, Dr. Luz, why is it that you put a parentheses and a Roman numeral for iron, okay? Can anybody guess why I had to put in parentheses that Roman numeral for iron?
Would that be the charge of the carbonate? No.
No, it's not the charge of the carbonate because it's next to the iron. Excellent. Thank you for the people that put it in the chat. Iron, because it lives in group 3B, has multiple charges. So I'm telling you what flavor of iron we have in this particular ionic compound. So that Roman numeral is going to be given to elements in group B because they need it. Remember, if you live in 1A, 2A, or 3A, your group number tells you what's going to be your positive charge. But then for group B, in parentheses, you need to be given what flavor of that transition metal we are working with, okay? So here we're working with iron 3. So what's going to be the symbol for the element and then the charge? So how do we illustrate iron 3? Great job. Iron is Fe, and then it has a charge of +3, okay? Carbonate, and let me give you guys just a little bit of like a hint. If for some reason you look at a word and you're like, oh wait, carbonate, that doesn't look like an element. Because I know that if you guys don't get familiar with all of this, then all of a sudden you'll be like, where is carbonate in the periodic table? Nowhere. Because carbonate, the elements that make carbonate are in the periodic table, but carbonate is not in the periodic table. This is why I encourage you guys to practice, 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 and get familiar with this. You guys have 2 weeks. Exam 2, if you're not ready, it's going to make you a brand new person. Because exam 2, we have so many rules for the naming that I encourage students, please practice the naming so you're not scrambling through tables. You know exactly where you need to look for the information. So carbonate is going to be in the polyatomic ion table. And thank you guys to put it in the chat. Carbonate is going to be CO3 and the charge is 2 negative, okay? Or -2, whichever way you want to write it. Now, as we have done before, this value of 3 is going to be the subscript of carbonate. This value of 2 is going to become the subscript of iron. Okay, so when we're writing this chemical formula, we are going to write iron with its subscript, which is going to be 2. We're going to write carbonate. Now, because carbonate is getting a subscript larger than 1, we need to put parentheses on it and then put the subscript outside. So understand, and let me just write it here in the notes. Parentheses are used around polyatomic ions when they have a subscript larger than 1. If your polyatomic ion has a subscript of 1, after we do the exchange, the subscript that is going to get assigned, if it's a subscript of 1, you don't put a parentheses on it. So it is incorrect to just put parentheses for the heck of it. No, parentheses only goes there if my subscript is 2 or more, meaning larger than 1. The Roman numeral just gave us a reference for the charge of our transition metal. That Roman numeral just gave us what is going to be the subscript next to the polyatomic. We're going to see that when we are doing the opposite. If I give you the chemical formula, but then you have to give me the name of that compound, then we need to incorporate those Roman numerals. Put a 1 in the chat if you're ready to practice. Excellent. There was a question in the chat. How do we determine the charge for the Roman numerals? In the exercise of I give you the components of the ionic compound and you give me the chemical formula, then you can see that you have the Roman numeral given. Next, after break, because we're going to practice this and then we're going to go on break. When you're given a chemical formula and you have to give it a name, then you need to derive it. But right now, in the process of, I give you the 2 components of the ionic compound and you give the chemical formula for the group B elements, you will see the Roman numeral. The only components of group B that I will not give you the Roman numerals is zinc, cadmium, and silver, because you need to memorize that zinc is always +2, cadmium is always +2, and silver is always +1. So let's go through these. In the first one, I will do the first with you guys, and then we're going to do the rest as a group. We have lithium and bromine. Lithium, the symbol is Li. It lives in group 1A, so it has a charge of +1. Bromine lives in group 7A, so its symbol is Br, and because it lives in 7A, its charge is -1. As I mentioned to you guys a few moments ago, if you have a pair of cations and anions, and the charges cancel each other, as you can see in this example, +1, -1. Or if you have +2, -2. Or if you have +3, -3. Your final answer is going to be just writing the symbols of the elements. Okay? Let's move to letter B. Put a 2 in the chat if you want me to do letter B. Put a 3 in the chat if you guys are ready for that. Okay, some people are ready. Excellent. I even see the answer in the chat. Let me explain why this is SRI2. Great job. So SR lives in group 2A. That's why it's 2 plus. Iodine lives in 7A. That's why it's 1 minus. So our final answer is SRI2, because this value of 1 becomes the subscript of the SR. Since it's a value of 1, we get omitted, and then this 2 is the subscript of iodine. Next one, manganese 4 and oxygen. What's going to be the chemical formula of that? When we have manganese 4 and oxygen. Great job. This is Mn plus 4, O minus 2. At first, we're going to do Mn2O4. Remember, this 2 becomes the subscript of that. This 4 becomes the subscript of this. Now, we are not done, because the 2 and the 4 are divisible by one another. So we divide both sides by 2. So that's why it's MnO2. Letter D, sodium and nitrogen. What is the chemical formula for that ionic compound? Sodium and nitrogen. Excellent job. This is Na plus 1, N, 3 minus, Na3, N. Next one, ammonium and phosphate. Ammonium and phosphate. Excellent job. Ammonium and phosphate. It's going to be NH4, positive 1. Phosphate is PO4 minus 3. So that means NH4 is now going to have a subscript of 3. But then PO4, since it has a subscript of 1, we don't put parentheses on it. Okay. Put a 1 in the chat if you need to see the highlighted arrows. I don't know if that's helping people or not. I'd include it. If not, I will not include it. Excellent. Let's do F. Iron 2 and oxygen. What is the chemical formula for letter F? Great job. So iron is Fe plus 2. Oxygen is O minus 2. As example A, the plus 2 in iron is going to be canceled by the O2 in oxygen. So our final answer is just FeO. Questions. If you're given the pair of elements or polyatomic ions and elements, or polyatomic ions pairs to make an ionic compound. Any questions on how to write the chemical formula? Excellent. So now we are going to go on break.